Yeah, so I think I'm now the kind of a last speaker in the session, and I mean Andreas gave a very nice intro to single photon detectors that already exist, made out of superconducting qubits, and so I don't need to tell you this introduction. And I'm also going to tell you about another approach that we can use for single photon detection, and we've shown something really exciting. It's not at the level of single microwave photons. Well, it is level of single microwave photons, but not as low frequencies as for qubits. But it's based on bolometer, and a bolometer is a very different type of a device. It's a thermal device, so it means that the microwave photon is absorbed and it heats up thermal mass, a very, very tiny resistor in our case. And then we measure with thermometry the temperature rise. So the bolometer is kind of that way very different, because it is basically like an environment for the photons that absorbs the photon instead of a coherent system that is, for example, the qubit detector. So for that reason, the bolometer may have advantages in certain applications. For example, it's typically very broadband input, like that we can make, you will see actually in one of my slides that we can make the band cover orders of magnitudes in frequency. And also actually it operates at very low power, and yeah, it's quite typically quite more simple device than a qubit, and it's, like I said, it's not quantum coherent, so you don't need to care about the coherence of quantum states. So this is a few things why a bolometer can be in some cases advantageous. Maybe one more thing is that it not only measures a click when a photon comes in, but you can actually use it also as a calorimeter. So if you don't know what's the energy of the incoming photons, you can also resolve the energy. So this is something that, for example, in these qubit detectors, you set the energy by setting the frequencies of the system, and then you are observing energies or photons with that frequency. Okay, but let me first thank some of the people. I put my group photo here into the front page, but it's not only my group who has contributed. We have had, for example, strong contribution to the graphene part from Pertti Hakonen's nano group here, and in general, we are part of the Center of Excellence for Quantum Technology here at Aalto University and VTT and University of Helsinki. And also, I would, of course, like to highlight VTT here, who has helped us, for example, in the choice of parametric amplifiers. All right, so let's move forward. Before I go into the bolometer itself, I wanted to highlight a use case for it. In this time, it could be, for example, using to read out superconducting qubits. The axions, I will say a few words in the end. Detecting the axions with the bolometer is a bit more challenging than reading out the superconducting qubit. So that's why I take the superconducting qubit as an example here first. So already you have been, in a couple of the talks, have been discussing or have been seeing that there's something called a dispersive coupling between a qubit and a linear resonator mode. This means that the resonator frequency here changes when the qubit state changes from G. And sorry about that. So basically you can then use this to read out the states of the qubit by shining microwaves in this transmission line and looking at the phase change of the microwaves after interacting with this readout resonator. And that's the standard way of doing it. And when you do it, you get this kind of dispersive shifts of the outgoing fields. So this is again in the IQ plane, so current charge plane, or you can call it real part or imaginary part of the annihilation operator as well. So you can see that these sort of the solid lines are the average trajectories of these two cases when I have the qubit in the excited state or in the ground state, and the dots are single shot readouts stuff. So you can see that depending on the qubit state, you have these trajectories, and there is less noise now, well less noise than what is the separation of these two distributions. So you can read out the state of the qubit by looking at them at the value in the IQ plane. Okay, that's the usual way. What we did is that we added another drive here to the qubit at the same frequency as this drive. So these two drives, they couple to different systems, and by choosing the amplitudes and phases correctly, we could make these distributions to behave very differently. So the trajectories basically go, vertically up or down, so they start to separate almost immediately when this readout signal comes, whereas in this dispersive case, it's just the frequency of the resonator is different, so you need to populate the resonator before this separation happens. All right, and we were able to measure that this kind of multi-channel way of driving gives you advantage in terms of speed or fidelity, and you can also do a trick where you choose the amplitudes and phases such that the ground state distribution stays close to zero, and then the excited state distribution goes out to actually pretty high photon number. If this calibration is correct, like we think it is, then this means that you have about 50 photons here with a lifetime of about 100 nanoseconds. And when I will come back to this in the end, and I will show you that this is well more than the energy resolution of our bolometers that we have estimated now. So this should be measurable. Okay, let me move now to the bolometers. So this no more qubits, but let's look at the bolometer. This is just an artistic image of the bolometer, and this is how it looks like in practice under the microscope. You can see these three ports, H, G, and P. G port is basically grounded. Sometimes it's grounded through a capacitor that you see in the circuit diagram, but we also currently we put it galvanically to ground just to make the grounding better. So if you have grounded this system at this point, it means that the input port, the heater port where the input photons come and absorb to the resistor, that port is kind of not electrically connected in the microwave sense to the thermometer side, which is here. So the way this works is that, as I said, the photons come in and heat this resistor. This is a small resistor. It's really resistive. There is no supercurrent essentially go through it, but then it heats up this resistor, and then the heat is equilibrating quite quickly in this whole nanowire. And these small normal metal parts here are actually proximity effect Josephson junctions. You have this superconducting aluminum that is galvanically connected to the gold palladium wire, and that the short distance here between the superconductors makes this little piece of gold palladium also superconducting. But the higher the temperature, the less it is superconducting. So the lower the critical current is, and the higher the inductance is. So that's the way we measure. That's the way we measure then the incoming power. So we look at microwave reflection from the circuit where you have this temperature-dependent impedance in an LC resonator, basically, and we measure the reflection coefficient as function of input power, or we can also, of course, change the fridge temperature. Something we have added now here relatively recently is a JPA. So we also use in this readout or this amplification chain JPA to get rid of some of the noise. It helps a little bit, not by a huge amount, but it helps a little bit to get the best results. But something to note here is that the heater input frequency here can be very different from the probe frequency. So this probe frequency works now at 0.5 gigahertz for us. You can choose it, you can engineer it like you want. And the heater works at about 8.4 gigahertz, but you can also engineer it like you want. Here is just some sort of phase of the reflection coefficient plotted as function of the frequency, and then the probe power. And basically we optimize the probe power such that we go into this regime where the resonance starts to shift when you increase the probe power, but doesn't yet become bistable. So there is kind of a resonance, but it's very sensitive now to small changes in the power. And what we do then is that we sit on one of these chosen points here close to that resonance, and we turn on the heater power, and we see then the output voltage to change. So the output voltage is the probe output voltage in the chosen quadrature. The other quadrature is essentially 0, and we have the voltage rise is basically there's an exponential rise to this plateau, and we then shut down the heater power and we see this exponential decay to this again the saturation value, and we measure here the thermal time constant, which is basically the exponential exponent in the rise. And then we measure the response, which is the voltage difference here. And then we, as a function of the maximum heater power we apply during the pulse, we can then plot the response. So we get the quasi-static responsivity, which is basically like at 0 frequency responsivity. And then we get the finite frequency responsivity by putting in the thermal time constant in the standard way into that. Okay, so this explains a little bit how to characterize the system, and we can basically now plot this responsivity as a function of the probe frequency and power, and we can see that again close to this point that I described earlier, you get some peaks in the responsivity. This is without the JPA, and this is with the JPA, and you can see that the color scales are actually on a very different scale. So with JPA, of course, there is much more response because the gain is high, but so is the noise density higher when you plot. Basically, we can of course measure just the noise in the voltage reading, and you can see that the noise is also higher with the JPA. And when you then calculate or extract the NEP with this formula square root of the noise density divided by the responsivity, you can see that the NEP is lower with the JPA, but not by a huge amount. Now the color scales are same; they are identical. So you can see that we can achieve actually very low noise equivalent powers, and if we take a trace here, for example, you can see that without JPA, we achieve a bit here over 40 zeptowatts over root hertz, and with the JPA, about 20 zeptowatts over root hertz in this optimal point. And these, when we measured these were the lowest ever measured NEPs for any bolometer. I think they still are, in fact. We also plot here the thermal time constant. You can see that it goes up to a millisecond here in the most sensitive point. And we will come back to this later on. But in the graphene bolometer, where the thermal time constant is much shorter. But we can count now kind of from the frequency dependent NEP, we can then extract with this formula what would be the energy resolution if we use this as a calorimeter. And we get about 0.3 zeptojoules. And this is still a relatively high value, and I will show you later on how to make that lower. So I so far just described like some characterization experiments, and now I want to show you some preliminary results on the detecting single pulses. So, but I think this is unpublished. So if you can pause the recording for a while, then I don't want to put this to YouTube yet. It might compromise the novelty of the results. So is there any operator who would pause the recording when I show the next slide, please? So we made also some experiments. This is not about the very sensitive bolometer, but this is about like a power traceable bolometer where we can really now very accurately measure what is the power absorbed by the bolometer, and the uncertainty there is very low. You can see that's our estimate uncertainty for that, and we can use this now, for example, to measure the attenuation in the lines coming down to the cryostat from room temperature. Actually, the uncertainty in our microwave source was quite high, so now the attenuation uncertainty is dominated by that, and you can see that now this frequency spans over 4 orders of magnitude, and the attenuation over 3 orders of magnitude and attenuation over 4 orders of magnitude. So so you can see that we can now use this as a tool to calibrate the lines, for example. Or if you want to calibrate your amplifier, you could perhaps use now a cryogenic detector instead of room temperature detector, which can be quite time consuming, etc. All right, so how would we improve on these numbers like I mentioned to you earlier? Well, what we did is that we replaced the gold palladium normal metal by graphene, simply because graphene has lower specific heat than gold palladium, so the heat capacity will be lower in the bolometer. And what we wanted to do is to do exactly the same device. Like we would have an absorber, we could tune it with this gate voltage, basically match the impedance of the absorber to the 50 ohm line, which is also a nice feature of graphene. We can tune the impedance by just the DC gate voltage, and then we can also tune the gate voltage here to make an optimal readout scheme. Well, unfortunately, the absorber port for us didn't work in these experiments, but then we went through a kind of a detailed calibration scheme where we could then use the probe port to heat the system using a slightly different frequency than the probe frequency, and that way we could then measure the NEP and the thermal time constant in the same way, basically as we did in the previous slides. Also note that it is possible to impedance match the graphene to a microwave resonator. It's, for example, done in this paper that was published back to back with our paper in Nature last year. Here is just some of these reflection coefficient measurements at different gate voltages and heater powers, and you can see that either with gate voltage or heater power, we can shift the resonance. And these are just the key results that we have at different gate voltages now on the thermometer part, and at 0 volts. I think it's kind of a coincidence that it's 0 volts, but still at 0 volts, you can see that we can reach an NEP that is about 30 septowatts over root hertz, so almost equal to the metallic device, and now without a JPA in the readout chain. So this is actually better than the metallic device without JPA, and the time constant is now very low. It's in the range of hundreds of nanoseconds. And for this reason, if we now plot this extracted energy resolution, it goes down to a single 30 gigahertz photon energy. So this is now a great improvement over the energy resolution and also on the speed of the bolometer. So I have here now summarized the whole table. I talked about the metallic bolometer. We can optimize it for low noise or for speed, because, well, if you look at this graph, for example, this typically at the lowest noise point, the speed is not fastest, or the bolometer is not fastest. So you can basically then optimize. You can compromise a little bit on the noise and get it even faster if you want. So these are just the numbers for the NEP and the time constant, and then the extracted energy resolution and then the measured one. And as I said, in the preliminary results, we measured about twice the extracted. So now it's quite exciting to see whether we could also measure now this single tens of gigahertz photons in real time. And we also want to improve this, of course, on this number, for example, to make this better for axion experiments. So yeah, what we want to do next is we want to now use this also in circuit quantum electrodynamics to measure these single microwave photons, and for the first time with bolometers. And also we would like to also, once you axion researchers think this could be useful in your experiments, we would be happy to give some devices to you guys. So I want to talk, and well, one thing to mention here is, now I'm coming back to the qubit readout sort of scheme, and it seems like that, yes, this 50 photons now is much higher energy than for example that we have got now as the energy resolution, or if you look at the NEP, the power is now so high that it should be able to sense it in quite short amount of time. So I want to thank all the people involved. This has been a nice collaboration, and thanks for your attention, and I'm happy to take any questions.
Thank you very much. Very cool and hard at the same time. So discussion is now open for questions. So please, from the audience.
Can I ask you a question?
Yes, please.
Yeah. Mikko, thank you very much for a very interesting talk. You show about first part of your talk. You show NEP at quite low level, but it's a continuous measurement of signal. And there is no sense in this NEP if you don't compare it with NEP of photon noise. What is your photon noise for this experiment? I mean, NEP photon noise.
Yeah, I mean, there is, I think, per se sense in saying what the NEP is, because first of all, we can tune this. I mean, the NEP is independent of the input power. So and the photon noise, the short noise of photons depends on your input power. So
yes.
So for us the photon noise is not a property of the bolometer, but it's a it's a property of what you're measuring. So that's why we go the NEP value of the device itself, rather than quoting some arbitrary value for the photon shot noise, which depends on what you're measuring.
Yeah, but it's always interesting to compare sensitivity of your bolometer and level of photon noise.
Yeah. So basically, of course, if you measure something that has very high power, and then of course the photon noise is dominating, and then your detector noise is very minor. So then you might want to use some other type of detector if that's more convenient for you. But if you want to sense really low powers, like for example in this axion experiments, we talked about octowatts. So there the photon shot noise is extremely low.
Okay, about your single signal, what number of photons were used in your input approximately?
You mean when we measured these single shots, the energies? That's okay. That's a good question. I can. So I think it is. Yeah, maybe of the order of 100 or some hundreds. I would need to make the math more accurately. Now I was just doing it in my head.
And in your final estimations, when you estimate approximately to what frequency you can go, how many photons were used in this experiment for these estimations?
In the estimation of the energy resolution, you mean?
Yes.
Oh, there is in that estimation there is basically no photon number doesn't come up in there, because you calculate the extracted energy resolution just from the NEP of the device again, which is independent of the photon number that you are sensing. So this is really now for thinking about single energy packets. So you could think about that you could be measuring single photons. Of course, if in practice, when we did this single shot experiment, we were sending in like pulses of coherent states. So you are correct that there is some photon number uncertainty or there, but that was like smaller than our device noise at those experiments. And in practice, when we do these estimations, like I said, it's basically meaning for single photons. So you don't, it's the energy resolution coming from the device, not from what you put into the device, the input.
Okay, thank you.
Thanks.
Yeah, so please, I see one more question. So please.
So Mikko, this is Song from CAPP. Thank you for the talk. So I have a very stupid question. So when you're talking about the NEP, can I interpret it as the intrinsic noise of your device?
Yeah, so basically you can think that it's the noise in our readout signal in the units of input power. So
right, yeah. So then you, as you just mentioned, well, typical reaction power is the yoctowatt, and then your noise level is the joctowatt, which is 10 to the 3. 3 orders.
Yeah, oh no, I was just making an example like that. Like actually, we in our case, we typically, if you looked at the graphs I showed, that when we heat the system, it's in the attowatt level, or even can be like 100 attowatt or hundreds of attowatts. So so that is kind of typical powers that we have been using when we are scanning these. I was just making an extreme example, saying that the photon or the NEP increasement coming from the photon shock noise at yoctowatt level is extremely low. But that's true. If it's 20 zeptowatts over root hertz, if you want to measure yoctowatt, that will then take a long time.
Very long time, right? Yeah.
Yeah.
Okay. All right, thanks.
Okay, any more questions from the audience? Probably have just a curiosity. So how do you estimate the efficiency in conversion between the radiation and the temperature or the heat that are going to measure? I mean, all these structures are suspended. I mean, do you have an efficiency of 100% that during the conversion from the photons all will be transformed in heat or temperature?
Oh, okay. So what is the absorption efficiency you're asking?
Yeah.
Right. That we can make very high. It depends now on the bolometer. In the graphene bolometer, because like I explained, our absorber didn't really work, so the efficiency was relatively low, not super low though, but anyways, not close to 99%. So, but we can make these. We have actually, because the absorption is based basically on a resistor, so we can match this impedance of the resistor very close to 50 ohms. And if you think about the power, the reflection coefficient in power, it's basically the difference of the characteristic impedance of the line and the impedance of the resistor divided by the sum squared. So if you have only if let's say that we have made resistors that are closer than 1 ohm to 50 ohm line, but 1 ohm would basically give you 4 nines of fidelity in the absorption. 4 nines, 99.99% absorption. So I think there will be probably more losses than coming, or more reflections coming from other parts of your system than from the resistor itself. But the resistor, that's a nice feature, that the resistor is so efficient in absorbing when you engineer it close to the characteristic impedance. And in the graphene case, as I said, you can actually then later on even tune the resistance with the gate, so that you can then go very close to the maximum absorption.
But the graphene is suspended in some way to use it as a calorimeter, or?
No, the graphene was not suspended in this case. It was on the substrate without suspension.
Okay, thank you. So let's see if there are more questions from the audience. Not so urgent. So I would like to thank again all the speakers and for very nice and exciting presentation they have. So thank you very much to everybody for listening. And so the workshop will continue tomorrow.